Hello everyone. So today we will be uh, talking further about gravitation. In the last video we have seen only the introduction part. I have told that the gravitation is always attractive in nature and always works in a straight line. So the first three laws are given by Kepler, and then Newton has done a great job in order to study the properties of this gravitational field. Now till now we have come across three planetary laws regarding Kepler, given by Jonathan Kepler. So the first law was that any kind of planetary object will move in elliptical orbit where the star will be there in either of these foci. So either it will be in here or it will be in here, and the planet will move around it accordingly. Acha. The second law of Kepler was given as the area swept by the planetary system from one position to another position will be same for same interval of time. That means the rate of change of area by time will be constant. So we are going to prove this little bit today, as I told you. So okay, now think that if the arc length is considered as a straight line, so it can be considered as a straight line when the planetary object has moved significantly lesser amount. So this curve line can be taken as a straight line. So I can say that if this distance is r and this distance is r plus delta r, and this one is, let's say, delta r, a change in length, whatever. So now what we can do, we can think that if the distance, this angle is 90 degree, so we can take this when the shift p to q is very less. So delta r is very less. When the delta r is very small, we can take. So I can write here that the area is half into the this one, that is the height. So the height can be taken as r into delta r, you can say. Okay, or even if you take r plus delta r as the height, then also there will be no problem. So okay, let us take this bigger one as a height. So let us take r plus delta r into delta r, that is the base. So this will be reduced to r delta r plus delta r square. So now you can see that this term delta r square is very small, because we have considered that this is smaller, so we can simply ignore this. So finally I can write that my this thing is r delta r. So this is my delta A because it is the swept area when it has significantly gone from P to Q with some displacement delta R. So from here I can write, because I need this delta A by delta T, so I can always write that delta A by delta T is half R delta R by delta T. So I can write this. So in the next page I'm writing here delta A by delta T is half into del R delta R by delta T. So that means this is your half r. Now this is my linear velocity v, you can write. Okay, now we know that for elliptical orbit, even we can write if the orbit is taken as almost like a circle, Then for simplification we can write that my L, that is the angular momentum, is mvr. So this is an approximate. I can only write whenever I am taking the orbit to be a circle, nearly to a circle. So Vr is L by m. I can put it here and I can write that this R will be then, so this I can write as L by m. So delta A by delta T, you can see L by m. Now one thing you note here, that in this motion nobody is pushing or pulling the planetary system. So there are like no external force that is working on the planetary system. So you can see here that my to rotate something we need torque, right? But here the torque is not there, external torque is not there. So this L, we can also write no this thing, because we know that the force is equal to change in momentum by time, right? Similarly torque is changing angular momentum by time. Now as there is no external torque, so my torque is zero. In this case external torque is zero, so my L is constant here. So as a result, this is a constant, this is a constant, and that's why this whole thing will be constant also. So we can say that the area, the rate of area swept by the planet while revolving is constant. Now you can ask me, sir, because we have taken here so many of consideration ki my delta r is very small. I have used a formula which is valid for the circle. So you can ask me, so this is a simplified form of the proof. There are advanced method, but that requires complexity, so I'm not going into that. This method is adequate for EO standard. So this was the second law of Kepler, okay, and the third law. Now we are coming to the third law. The third law of the Kepler was that ki when that thing is revolving, so the time for one complete revolution is related with the average distance with this formula. Now we are going to prove this. But to prove this, we need Newton's gravitational law, because with that, very easily with classical mechanics, we can solve this problem. Now, let's say something is revolving in this uh, almost circular path. Again, we are taking assumption for our simplification, and the star is here and it is moving. The radius is, the orbital distance is r, or you can say the radius is r. So we know that when something rotates, the two kind of forces are acting on it. One is the gravitational force that is being worked on the planet by the star, and because it is rotating, so obviously a centrifugal force will be acted on the planetary object. So I can say that the centrifugal force Cf will be same as the gravitational force, gravity. So I can always write, in order to maintain the orbit, in order to uh, have a fixed orbit, otherwise the planet will go farther from the star or nearer to the star if this thing is not in equilibrium. So what we can do here, we can write that mv square by r is equal to g into big M. So I'm writing here big M, small m. Big M is the mass of the star and small m is the mass of the planetary object, by r square. I can write, so even I can cut this to m because they are same. Now v square is equal to, also I can cut this r and this one r, okay. Achha, this distance is taken from center of mass to another center of mass. So it is, this r is from the center of mass of the star to the center of mass of the planet. So I can write that v square is equal to gm by r. Now you see one thing, that v can be also written as the velocity is distance by time. Now the total distance is 2 pi r, that is the circumference of this whole orbit, divided by the time itself, that is the time period. So v square, I can just write v square is equal to 4 pi square r square by t square. So this thing I will write in that side. So I'm writing here 4 pi square uh, r square by t square is equal to gm by r. So I can write from here that t square is equal to 4 pi square r cube by gm, which proves that t square is proportional to r cube when the orbit is almost nearly to a circle. So this is, we have to do this derivation, we have assumed that the orbit is a circle, but it is not necessarily has to be a circle, it can be ellipse also. But so that we don't have to do complex mathematics, that's why we have taken a circle and we have proved in a classical way. So these two things are the proof for Kepler's law of motion. So this is the third one, and this is the second one, and the first one is just the incident key. When a planet is rotating, it will orbit in a elliptical orbit, and the star will be in either of the foci of that ellipse. So now we are moving, so this was the Kepler's one. Now we are again coming to the Newton's gravitational laws. In the last lecture, we have seen that the force given by Newton, so this is the property of gravitational force that Newton has seen. We have seen this. Now there is something which is called gravitational field. Now what is gravitational field? The gravitational field E is force per unit mass. So that means if I bring 1 unit mass in front of another mass m, so that E will be g, that big M by r square. Okay, so we can say that the relationship between the force and the field is so this is the gravitational field. So the relation between them is E is equal to force by the mass which you are bringing. Now this gravitational field is also called gravitational strength sometime. So this E is a quantity that measures the strength of gravitational influence of any material over another material. Okay, so this was another thing we need to know. One more thing is there which is called gravitational potential. Now what is gravitational potential? Now you see that if we have two objects, like this is one object and this is another one, this is having a mass m and this is having a mass small m. So now you see that gravity always pulls, right? So if this small m is far away from this big M, the big M and the small m will have pull towards each other. So this big M will be pulled by small m and the small m will be pulled by big M. That's why they both will come closer to each other. They will come closer to the center of mass of the system. So we have to see that where is the center of mass of this two system. Let's say this is the center of mass. So this big M will come also here, and this small m will also come here. Okay. Now, so you can see that they will come automatically. You don't have to bring them. As you don't have to bring them, that means this system of two planetary objects will do work automatically. That means the system will develop the work. That means the system will give you the work. Okay. And whenever the system is giving us the work, or the system itself is doing the work, we tell that this work done is negative. So when we take work done as negative, that means that it is not negative energy. That means the work done is done by the system. Okay, so the work is done by the system and we are getting the work. So it means that. Okay, so we know that, so we can directly prove this. How we have to prove this? We have some definite relation also. So the gravitational potential energy is uh, so I'm writing here GPE, gravitational potential energy. So this is given by the definition is given by when you bring any mass from infinity to a distance r from the sorry to a distance r from the object, from any other object. So I am bringing in this case this mass, small mass m, to a distance to at a distance r from the big object, then the work done by the system is called GPE. So this is the work done by the system to bring small m at a distance r from the big M mass from infinity. So this is the definition. So what is the measure? What is the formula for that? Okay, so we can directly find out this. We know that the work done is force into displacement, right? So for a very small displacement dx, the work done is dw. So now I know that the force for gravity is gm m by r square. So we have taken x as a parameter, so I will write x square dx. So this is my dw. So if I do the integration here, I told you that I have to bring from infinity to r. So from infinity to r I am bringing. So my work done will be given by, if you do the integration, the result will be g minus gmm by r. So you can see here this thing is given by, is like this relationship gives us gravitational potential energy. Okay, this thing gives us the formula for gravitational potential energy. Now I told you in the earlier class that potential energy is an energy that is owned by the system because of its configuration. So you can see here also that this is the big mass and this is the small mass. So if the small mass is there at a distance r, so see, it will automatically come to the big mass, right, and collide. So if this small mass has to stay there at a distance r from the big mass, it must have the energy required to stay there, right? Otherwise, if it does not have any energy, it will just directly go and fall into the big mass. So this energy which this small mass is having while staying at r distance from the big mass is the gravitational potential energy, which is given by this relationship. Okay. Now one more term is there which also measured the influence of gravitational uh, like pull or the gravitational field of an object. So that is called potential, like only gravitational potential. Gravitational potential. The energy term is not there. Okay, so gravitational potential and gravitational potential energy, these two terms are different. Okay, so the gravitational potential is again the similar like gravitational field is nothing but the gravitational potential energy. Okay, so I am writing here gravitational potential energy divided by the unit mass, that means divided by the mass. Okay, so the definition is like that key, the gravitational potential energy per unit mass is called gravitational potential and it is denoted by V. So this is also negative because the work is always done by the system, because the system is attractive. Gravitational field always attracts things. That's why the values of V is negative always. So this thing is called gravitational. Sorry, class. Okay. So gravitational potential. Now one thing you can see here, if I write the relations, so you can see that the force and the field is having this relationship. Okay, and as well as this gravitational potential energy, that is W or JP, whatever you write, is equal to the V into M. Okay, so the force and field are the same thing, but the field is the force on the unit mass. The gravitational potential energy and the gravitational potential are the same thing, energy only. They are energies, but the gravitational potential is the energy per unit mass. The terminology is different, but the physicality is same in the both cases. One more interesting thing or the term I will use here, that is central force. I told you in the last class that I will be telling you this one. Now central force is those force, the central forces are those force which have a very unique property. So if you see that this relationship, we can see here that our V, if you tell the V or if you tell the W. So if you are taking unit mass, so W will become V automatically. So you can see that this V, gravitational potential, is proportional to 1 by R. So it is a function of R. So whenever for some force, the potential is a function of distance and is negative in nature, those forces are called central force. So that's why gravitational force, okay, because the gravitational potential is negative and it is dependent on the distance from the object. That's why the force, because of this potential, is called the central force. So that's why gravitational force is a kind of central force. Also, gravitational force is called conservative force. Why? Because if you do some work, it will give you back the same work. There will be no loss of energy or no dissipation of energy, if I say better in a better word. no dissipation of energy, whatever. So if I had to give one example, I will say that if you have a ball and if you pull the ball up at a height, so this is the, so if you are pulling the ball at some height, so that means you are giving some work done because you are pulling against gravity. And then if you just leave it, it will automatically be attracted due to gravity and it will come down, and it will return you the work as kinetic energy. It will return you the same work what is done by you. Now see, if you can talk about air resistance, but if you are doing the whole experiment in a vacuum where there is no other forces uh, rather than gravitational force, then if you do some work on the system which is there in the gravitational force field, then it will return you the same amount of work which you have given, and that's why it is called conservative force field. So gravitational force is a conservative force, and also it is called a central force, okay, because the potential due to this is negative and a function of r. So today we have seen quite a bit of things. uh, Central force, we have seen the derivation of Kepler's law also, and what is left then? The left part is G. Last day we were talking about the gravitational acceleration. If we have any object on our earth, above our earth, then it will automatically drop down, like it will automatically uh, fall. Now it will fall in some force field, so that's why there will be acceleration. Now this acceleration we have seen the value is gm by r square, right? We have seen in the last class. Now the question will come, we can see that g is dependent on r, that is the distance from the center of mass of our earth to that object. So we write always g 9.8. Is that correct? Is the writing g equal to 9.8 is correct for all the time, or g varies with height and depth, and how it varies? So the next day we will be looking at this thing, and then the most of the chapter will be covered and we will be ready for our discussion and numericals. So bye bye for today, and I will see you in my next class.